Alright, so the end is in sight. Good. So where we got to last time was, the idea was, okay, so again, once again, trying to classify phases of matter, and we're looking at these black holes, right? So we had our extremal black holes, electric field, and near horizon geometry, parameterized by z and theta, the Lattices exponent and the hyperscaling violating exponent. And what we were setting up this morning was that we wanted to probe these phases of matter described by these black holes by the current two-point functions. Right? So we've been talking about the retarded Green's function, the function of omega and k, for things like the density two-point function. And the main message of this morning was that what's really important is the imaginary part of the retarded Green's function, which is also called the spectral weight, and that we're interested in the low frequency behavior of that as a function of k. And what I told you right at the end was that this is determined by the near horizon geometry. So the plan this time is that we're going to, first I'm going to motivate and write down some answers, what you actually get for this guy, okay, what this actually looks like. And then secondly, we're going to see what this is good for. So the plan for the next hour is, so we're going to compute, or rather I'm going to tell you the answer, this guy, for different values of z and theta. And we're going to see what that tells us about the phase of matter. And secondly, we're going to use it, we're going to use this quantity to compute some connectivities. Which are, of course, very physical things. Good. So actually, were there any questions from this morning? So let's calculate the retarded Green's function from the IR. So it splits into two cases. The first case is when z, this dynamical critical exponent, is finite. Then, by scaling, we know that the retarded Green's function of omega and k, remember that this IR geometry has this scaling in it. And so I'm using the fact that it's determined by the near horizon geometry. So this guy has to be some function of k to the z over omega. Right? That's the scaling, the relative scaling of space and time. And then there's some overall exponent, let's call it omega to the delta. So the scaling symmetries of the near horizon geometry mean that the Green's function, the IR Green's function, has to take this form. Okay. Now, in fact, and now we want to take omega to 0. Okay. So when we take omega to 0, okay, this is fine. That's just some power. But what we really want to know is what happens to this function, right? This function of some function of x. And so omega goes to 0. Of course, implies that k over omega goes to infinity. We're at fixed k. Okay, remember the name of the game is we're looking at how the spectral weight is distributed as a function of k at low energies. So what we want is to know how this function behaves at large x. All right. And so that's the same as fixing omega and setting k to infinity. All right. Now remember that the way we got this Green's function was by solving a wave equation in this near horizon geometry. So that was box phi m squared phi, where actually phi is essentially AT. Okay. So this thing will certainly be some derivatives in R. There'll sort of be an omega squared, and there'll be a k squared, very schematically. Okay. So that means this derivative has derivatives in x, t, and r. And so now, when k is large, so this limit is a large k limit, that's basically a WKB limit of this equation. So k large, k over omega, well, k large is a WKB limit of this equation. So let me say exactly what I mean. So remember what WKB is, something that hopefully you saw in quantum mechanics at some point. Now, but what it means more generally is whenever you have some differential equation that looks a bit like this, and one of the coefficients becomes large, okay, the way you solve it is by taking your field phi to be e to the k, the large parameter, some function s, right? You're trying to find phi of r, and you do that. Right, so in quantum mechanics, this would be like s divided by h bar, right? And h bar is getting small, okay? WKB is like a semi-classical expansion. So now we have the k here. And then the point is that exactly, well, I'm sure you all know. So then what happens, the second derivative term becomes two terms. There's a k s prime prime, and then there's a k squared s prime squared kind of term, right? And so at large k, you keep this one, and that balances this guy in the equation. And the upshot of all this is that you find a solution of the form, right? So phi goes like sort of e to the plus minus k integral, doesn't really matter, some function of r. The only thing, I'm only trying to make one very simple point here, okay, is that when k becomes large, it's natural that the solutions will have a k in the exponents, okay, because you need to try to balance this k. So, in fact, in this limit, in this large k limit, you can just completely solve this equation. You can solve this wave equation. And I'm not going to do it, but you roughly use these kind of techniques. So, some dots. And what you find is that the Green's function, this function of f, of k to the z is of omega, the imaginary part, right? So that is exponentially small. So it goes like e to the minus k c to the omega. It turns out it goes like this. So we're going to understand this in 1 second, okay? So what have I just told you? Okay, so if that made sense, what I'm telling you is that when in the geometry, when z is finite, okay, the imaginary part of the retarded Green's function goes like this, right? And you just have to believe me that you can get this by solving this equation in a certain WKB limit. Okay? And it was the fact that because z is finite, this ratio has to appear. K to the z has to come with omega. And when you said omega small, it's the same as taking k large. K large pushes you into this WKB regime, and with really somewhat minimal work, you can solve the equation, and you get this. Now, what's the point? The point about this is that as omega goes to 0, this just goes to 0. Okay. So this says a very simple thing. It says that if z is finite, there is no low energy spectral weights at k at non-zero momentum. Okay. Which is honestly, if you didn't have you could have guessed this from the beginning for the kind of things I was saying this morning. So when Z is finite, the dispersion relation is omega goes like k to the z. Okay, so if you want, these are like the on-shell particles, want to have this dispersion relation, and that means that whenever you have finite momentum, you also have finite energy. And so if you ask, well, how many low-energy particles are there, low-energy excitations with finite momentum, the answer is 0. Okay, because if you have momentum, you also have energy. Okay, so the upshot is that, therefore, all these black holes, all these geometries, any space-time where z is less than infinity in the IR, they certainly have nothing that looks like a Fermi surface. Because remember, a Fermi surface was precisely the existence of low energy degrees of freedom with finite momentum. Okay, that's what we saw this morning. Okay, so these guys just look like something from Mars. Okay, they don't look like any state of matter that anybody has considered. Right? Okay, now,
Sean, in all of this, you're implicitly assuming that z is greater than 1.
No, so all states of matter that are fermions are constructed perturbatively, so have a Fermi surface.
No, I mean I agree, but when you solve the equation the way you described, you're assuming that z is always greater than 1, because otherwise your power, the exponential will...
Sorry, that's a good point, actually. No, I think I would assume it was positive, in fact.
Because then the power in the exponential will get reversed and you won't...
Actually, that's an excellent. That's a good point. Actually, let me make a comment about that. So, indeed. So in all known physical cases, in holography, z is always bigger or equal than 1. Okay? However, so what does this mean? So z is the relative rate at which time and energy scale. Okay? And so let's have an aside. Z negative, that would be very weird. Okay? That means that as you start, well, that basically means that short wavelength degrees of freedom would have low energy, and long wavelength degrees of freedom would have high energy, right? Yeah. So Z negative would be some dispersion like omega goes like 1/k or something. Okay, seems a little weird, but actually possibly relevant to things like localization. But let's leave that for the moment. Right, because if all your low energy degrees of freedom are localized in space, then that's precisely a short wavelength picture. But okay, so Z negative seems a little weird, but what's not so obvious is that you couldn't have a Z that was between 0 and 1. So that means that time and space are still going in the same direction. It's just that, well, one scales faster than the other. I'm not sure which one it is. So this a priori looks like it could be possible, but I'm not aware of any either conventional or holographic condensed matter system where you land in this regime. So actually it's an interesting question. If you can this exist? Like, I don't know, non-pathologically. Thanks. Good. But now what I want to spend the rest of the time talking about is this miraculous case where Z is infinity. So what if Z is infinite? Okay. So this is very interesting. Firstly, in holography, because this is actually the first thing you get. Okay, so you're string theorists, you know nothing about condensed matter physics. The first thing you write down is Einstein-Maxwell theory. Okay, that's the simplest theory in the bulk, right? So the simplest, with no scalar, just Einstein-Maxwell constant. In this case, the extremal black holes are horizon motion ADS black holes, and the near horizon geometry, as I mentioned yesterday, the near horizon geometry is ADS2 cross R2. And this, as I also mentioned, has z equals infinity. So z equals infinity is a scaling. So z equals infinity means that time scales, but space doesn't. Okay. So the general metric that has this form is you can have some hyperscaling term, and then you have an ADS2 and the R2. And again, this has a symmetry. T goes to lambda t, R goes to lambda r, but x not a symmetry. It has a scaling action where time scales, but space doesn't. Okay. So the overall metric scales too. All right. Now, we might expect something interesting to happen in this case, because the fact that space doesn't scale means that momentum doesn't cost energy. Okay, because the scaling. So basically, that means exactly you scale using this symmetry. You scale to low energies, but your momentum stays the same, right? So yeah, again, momentum doesn't cost energy when you have one of these symmetries. And so if momentum doesn't cost energy, you might expect to get some low energy degrees of freedom at finite momentum. So let's see what you get. So again, I don't have time to solve the equations, but you'll have to believe me that if you solve Maxwell's equations in this background, okay, and calculate the Green's function in the way I described this morning, so now it's not going to be of this form. You don't have to have this form because z is infinity, right? So that means k is dimensionless. And so what you get, the imaginary part of the retarded Green's function in this case happens to take this form, some function of k times omega to some power that also depends on k. Okay, so this thing was sufficiently exotic a few years ago when people came across it that they gave it a name, and this was called semi-local quantum criticality. So this name is due to Iqbal, Liu, and Zai. And so what's the point? So there are three words here, okay? So quantum critical is just the fact that it's a power law in omega, okay? Local, okay. What they mean by semi-local is that, well, local is trying to say that the momentum dependence is weak. So local would be if there's no momentum dependence, and semi-local is just the fact that there's a weak momentum dependence in the exponent. Okay. All right. So again, this form of the Green's function is only possible because there's a scaling symmetry where space does not scale. Okay, so the omega and the k's don't have to go together; they can be separated. So, yeah. And so now, if you plot this, the natural quantity to plot is this imaginary part. You need to divide by some power of omega. Take the limit omega goes to 0. So this is the low energy spectral weight. This thing here is just a dimension of the operator. Okay, so this is saying, this can seem strange. Okay, this says that the scaling dimension of the current operator depends on the momentum. It's a momentum dependent scaling dimension, right? That's what this delta of k means. And if you want to think of it in terms of wave equations, it's quite easy to see where this comes from. You have ADS2 cross R2. The k is the Kluter-Klein momentum along these x directions. That appears as a mass in ADS2. Okay? And as you know in ADCFT, the scaling dimension depends on the mass, right? So the scaling dimension depends on k in this case. It's like in ADS5 times S5, the scaling dimensions depend on the harmonics on the sphere, on the S5. Okay? The S5 now becomes this guy. Okay, and so, okay, here's the cool thing. So this plot, it turns out, if you plot it as a function of k, it looks like that. All right? That's this function, basically, that we're plotting. And so what this is very nice, because what this looks like, remember, this morning when we did free fermions, right, we plotted basically this quantity against k, and we found that it went to 2kf, right? There was this, and then it dropped to 0 at 2kf, right? That was what this was free fermions. And so what this looks like is, it looks a lot like a smeared out Fermi surface. So, this is really interesting. The reason it's interesting, let me try to convey why this is interesting. Okay, so momentum costs energy, right? It's kinetic energy. Now, so how do fermions manage to have low energy excitations at finite momentum? They do it because of Pauli exclusion, right? Indeed, your fermions want to all sit at 0 momentum, but they can't because of Pauli exclusion. And so you build up a Fermi surface, and the result of that, as we've said many times, is that the low energy excitations live on the Fermi surface, not at the origin. Okay. This is some extremal black hole. Okay. It doesn't know anything. I haven't mentioned the word fermion. I take Einstein-Maxwell, this theory. Okay. I solve it. I find this black hole, and now I'm looking at its spectral weight. And it turns out that this black hole supports low energy excitations at finite momentum. Okay? So it's as though there's something like the Pauli exclusion principle that's at work with this black hole. Okay? But it can't literally be, it's some strongly coupled version of it, right? So it's sort of suggestive of some strongly coupled non-quasi-particle. So quasi-particle just means particle. Non-quasi-particle version of Pauli exclusion. So black holes are somehow able to put low energy excitations at finite momentum. Okay, that's what I'm saying. Okay. Questions?
Sean?
Sorry? Excellent. Yeah, excellent. Good. Sorry. Okay, exactly. So what you exactly good. So to get back, take a little detour, but I'll come to your point in a moment. Okay. So let's get back to the big picture, which was that we wanted to classify phases of matter, and how close. So you could ask, how close is this to a Fermi liquid? Is this how precise? Is this really some strong? Is this what a strongly coupled Fermi surface looks like, or is it something else? Okay. And one way you could ask this is there something like a Lattices theorem for this shape? And remember, the Lattices theorem was a statement that the charge had to equal the volume of the Fermi surface. Okay. And to get the volume of the Fermi surface, I need to tell you this is like kf squared, right? It's whatever, pi kf squared. Okay, so I think what you were asking is there a kf that you can extract from here? And right, actually that's not very clear. So it turns out this decays exponentially at large, so it goes like e to the minus k, over some k0. So there's some characteristic width. Okay, and so you'd be very tempted to call this guy kf. Okay, that you could define. So this is a kf not defined through any fermion Green's function. Because fermions are like weakly interacting concept. Okay, that have these single particle fermion states. Here I have a more collective thing. Let's say I call that kf. Can I relate that to the charge or something in some way? And I just don't know. Right? So that's so it's another question you could ask. Again, trying to understand how similar this is to a fermi-liquid, as if there's some analog of the Leibniz theorem or not, for example.
Sean, so these semilocal equal geometries, we know they could also occur in phases where you have a broken U1, which would be closer than to what you would expect for a superfluid. But would you expect then that the spectral weight would still look the same?
Yes.
Because then, on the one hand, you would more expect something bosonic.
Yeah. Right. No. Okay. So what Blaise is saying and what this relates to. So remember at the beginning I was separating all these different cases. So I was saying, okay, you have some space-time. The charge can be inside or outside the black hole. If it's outside, it can be bosons or fermions. Okay, I had all these 3 different cases. Of course, in general, you can have mixtures of the 2. Okay, this is what Blaise is referring to. But then, nothing really new happens. So there'll be some charge behind the black hole that you can think of like this, and the charge outside you think of as a superfluid.
I really meant that you could find an IR geometry for a purely cohesive case with exactly those symmetries.
Yeah, let's talk about that later.
Okay.
Right, because I want to spend the last half an hour on something a bit different. Well, so I want to use this. Okay. So suppose what does it buy you? So suppose you have a non-zero spectral weight. At finite, at omega goes to 0, k with finite momentum. So it turns out there's a couple of very cool things that follow from this that have to do with transport, and so that's what I just want to talk about that a bit right now. So let's talk about conductivities. So, remember high school or something? There's something called Ohm's law, right? That relates the electric field and the current that defines the conductivity. Okay. So first, let's get the formula for the conductivity sigma. Okay. So let us work in a gauge where AT is 0. And the electric field is the time derivative of AX, which is I omega AX, some minus signs. And now that means that we just divide this by here, and we'll get that the conductivity is J divided by I omega A. Right. But we know that the vector potential is a source for the current, so J is the retarded Green's function of the current times A, by the definition that we gave this morning. So the A's cancel, and so the upshot is that the conductivity as a function of frequency is the retarded Green's function of the current operator divided by omega. Okay. So to calculate the conductivity of a system, all you need to calculate is the retarded Green's function of the current. Okay. Which is great because that's just exactly what we've been talking about. Okay, so this is the field theory definition of the conductivity. Okay, so suppose now let's take one of these black holes, and I've been telling you how to calculate Jx, the two-point functions. Okay, you have to solve the Maxwell's equation of the bulk, impose infalling boundary conditions, take these two guys at infinity, take the ratio. Okay, everything that we said this morning. So what are you going to get if you calculate the DC conductivity, which is the limit as omega goes to 0 of the conductivity? You're going to get a very simple and unpleasant answer, which is that it's infinite. Okay. So what went wrong, as it were? You set up a black hole, it had these beautiful spectral weights, it looked like Fermi surfaces. But if you calculate this two-point function, which is not difficult, okay, solve some ODEs and divide it by omega, you'll find that it's infinite. Right? And so this happened because for a very good reason, which is that momentum is conserved. Okay? Which, as you know, that's a consequence. The fact that momentum is conserved is a consequence of translation invariance. So that's a stupid thing. Suppose you have a medium, you have your metal here, you run against the medium, okay? You'll see a current coming towards you, but you didn't apply any electric field. Okay, so clearly you got a current with no electric field, so the conductivity must be infinite. That makes it sound like a boost. It's not the boost symmetry that's important. It's actually translation invariance. So the picture, this is the picture is the following. So by the way, there's a lesson here, okay? You'll see many calculations in condensed matter papers of conductivities that don't break translation invariance anywhere, and they should be suspect, okay? It's not, if you don't break translation invariance, your conductivity will be infinite, right? That's a fact. And so the picture you have in mind is the following. You have time. So at weak coupling, you can sometimes get away with forgetting this fact, but at strong coupling, it'll bite you in the face. And so the picture is the following. Suppose you have some current J. You set up some current. When you set up that current, that will certainly also be carrying some momentum, because any state that carries current, and these setups will also carry momentum. Now, the momentum is conserved, so that doesn't decay with time, right? So momentum commutes to the Hamiltonian. That's 0. Now, what about the current? The current is not a conserved quantity. Okay? Remember, the charge is conserved, Jt dot is 0, but J, the integral of the current, that's not a conserved quantity, right? Remember, don't get confused, d mu, J mu is 0, but that means that Jt is conserved, not J, right? J dot as an operator is not 0. Okay. So what will happen is your current will start to decay. But then, because the momentum is still going, it's going to drag. It'll drag the current along, and the current will never go to 0, right? Because the momentum is conserved. And the fact that the current that doesn't relax to 0 is the same as the conductivity being infinite, because here you have a steady current with no applied electric field. Okay, right? So if you don't break translation invariance, the conductivity will always, I promise, be infinite, okay? With one exception. So you can put some equations behind this picture. Which I'm not going to do. But what you'll get if you do that is that the conductivity includes a term that's a delta function at omega, and the coefficient is a certain susceptibility. So what this is a quantity that measures the overlap between the current and the momentum. That tells you that if I have a state with a certain amount of momentum, it'll have a certain amount of current. So as long as this is not 0, well, this can be 0 if, it can be 0, but in a metal, it's not 0. Okay? So this tells you that any state that carrying current also has momentum. It's pretty reasonable. So roughly with this picture and some very, very simple manipulations with Green's functions, you can show that the conductivity has to be infinite. Okay? Because again, I'll say this one more time, the current cannot decay because it overlaps with the momentum. Given this is meant to be a score of integrability, let me open a little bracket here. Of course, if you have an integral system, it's infinitely worse because you have infinitely many conserved quantities, not just the momentum. Okay, and any of these conserved quantities. So in fact, in an integrable system, sigma of omega will be something like the sum of all the conserved charges that overlap with the currents times the delta function. Okay. But to be infinite, you only need one thing that lives forever. But if it's integrable, there are many, many more. Right. So, and this is also interesting. So that means that if you want to, in a minute, we're going to break translation invariance, okay, to relax the momentum to get a finite connectivity. But if you have an integrable system, you need to add some you need to break all of the charges. Okay. And actually, people use this to calculate the connectivity. So we have weakly broken integrability. You can calculate the connectivity. It will depend on the rate at which these integral quantities are not conserved. Okay. But okay, let's just think about momentum. So to get a finite conductivity, we need to break translation invariance. Okay, it's a requirement. Right? So it might seem right. Now this is where life looks like it's about to get messy, because there are two ways in the real world that translation invariance is broken. One is through disorder and impurities. Okay, so that's just the fact that you've got lumps of stuff around. And the other one is through the fact that most of condensed matter physics is happening on the background of a lattice. So there's certainly a lattice of ions in the background that gives you a periodic potential that also breaks translation invariance. Okay. So if you want to get a finite connectivity, you have to take into account these effects. Okay. Now here's the fun. Okay, here's an interesting thing. So let's think about lattice first. Any questions? I guess I should say. So for quantum field theorists, you might say, well, don't tell me about lattices and impurities. Okay, well, what are these? So these are perfectly something you can perfectly well include within quantum field theory. So let's think about the lattice case first. So in quantum field theory, a lattice just means you add a periodic coupling, a space-dependent coupling to your theory, right? So you've got some theory of dx dt, and you add a term to your action that may be something like, let's just be in 1D for simplicity, cosine kx times your operator at x and t. Okay, so there'll be some operator in the theory that couples to the lattice, and that will have a term like this. For disorder, instead of a nice cosine, you have some very complicated disordered potential dx. Okay. Note that these guys depend on space but not time, right? So these are what's called quenched impurities. Where do I want to go? Right. So now there are two possibilities. So you've got your quantum field theory. Okay, you will have your quantum field theory. You add a term like this, and two things can happen. Okay, either these couplings are relevant or they're irrelevant in the quantum field theory sense of the word. If they're relevant, we're probably screwed, because that means that as you flow to low energies, the bumps are becoming bigger and bigger, and you shouldn't use quantum field theory anymore. You should go to some other description. So if the lattice / impurities are relevant, I mean this in the technical quantum field theory sense, which unfortunately I don't think I'm going to have time today to actually derive what that means, but there's certain criteria. this means that the low energy physics is very inhomogeneous. And that means you're going to land up with all kinds of lovely physics, such as localization, glassiness, etc. Okay? Insulators. This is all beautiful stuff, but it's mostly outside the regime of quantum field theory, right? Because the inhomogeneities you certainly don't have a gradient expansion, right? Because the inhomogeneities are huge. However, what can also happen is that they're irrelevant. And that means that we can treat these as a perturbation at low energies. They're small, and so you can treat these translation breaking effects as perturbations about a homogeneous background. So if they're irrelevant, you can treat as a perturbation. And this is actually a very nice example of something that's dangerously irrelevant. Well, yeah, okay. A slight abuse of the word, but let's do it. In the following sense, that they're irrelevant, so their effects become small at low energies, but if you take them out altogether, the conductivity is infinite. So it's an irrelevant operator that you need to include to see the effect, to see the degradation of the current. In particle physics, this might be like proton decay, right? So there could be some high order operator that causes protons to decay. It's irrelevant, but if you want a proton to decay at all, you need these operators, right? So if you want your current is exactly conserved, the momentum is conserved, that makes the conductivity infinite. So if you want the conductivity to be finite, you need to include these effects, even though they're irrelevant in an RG sense of the word. Okay. Yes. You go first.
Why the conductivity should be infinite in the conservation invariant system? For example, we can get the classical Wilson equation, which is obviously a conservation invariant, and then we get some kind of value of conductivity which is proportional to rho.
Yeah, so this is the kind of thing that I was saying. So yes and no. So if you write down in fact you can prove from if your Boltzmann equation is translation invariant, the conductivity will be infinite if you calculate it correctly. Now, if you make an approximation, you can get a finite conductivity. Now, that finite conductivity is sometimes the right answer anyway. Okay, in the sense that when you add it has. Okay, let me. It's a bit of a tangent, but it's pretty interesting. So here's a canonical thing that people do. Is they say, okay, I've got my electron. All right, the electron scatters off something, some self-energy. This is the diagram, right? This gives me the self-energy of the electron. This will have an imaginary part. It will certainly be finite. I call that the lifetime, the inverse lifetime of the electron, right? It's the rate at which it's scattered and stuff. Then I take this lifetime and I put it into a Drude formula, which is n e squared tau over the mass of the electron, okay? And voila, finite conductivity, okay? Now, what did I secretly do when I was doing this? So this is the conductivity. Remember the conductivity is Jx, okay? So, yes, and Jx is basically psi dagger dx psi. Okay, so this conductivity, what I secretly calculated was this diagram. Just free, right? Remember, this is Jx. Oops. Each x is 2 fermions. You calculate this diagram, and I plug in. When I do this diagram, I plug in this propagator, which means I'm calculating that diagram. Okay, so if I do that, I'll get this answer, all right? And it's translation invariant, so what's wrong? Well, what's wrong is that you missed another diagram, which is this one, okay? When you do that, you put them together, you're getting you'll see that the connectivity is infinite. Okay, so actually, sorry. What you really did was you resummed these diagrams, a bunch of, these diagrams. And so what you have to self-consistently do is include these diagrams. When you add both of them, you'll get an infinite connectivity. And many treatments of the Boltzmann equation don't include vertex corrections, so you're basically ignoring this diagram. Okay. So now, what? Yeah, there's like thousands of papers. Okay. Now, most of the time it's okay, right? And so the reason it's okay is just totally technical. This is interesting. So let's talk about this. So what is, let's say you're doing Fermi liquid theory, so you just have electrons, weakly interacting electrons, and the interaction is sort of a 4 Fermi term. Okay? Then the self-energied electron comes from this diagram. Okay? That's due to this interaction. That's the equivalent of what I just wrote there. But let's say you're scattering off the only electrons, so you're scattering off other electrons. What do I want to say? Okay, to cut a long story short, what often happens is that the rate of momentum relaxation is the same as the lifetime of the particles. So when you have the two effects, you have momentum relaxation and you have just a decay of the particles, you get the same answer. You get the same, because it's determined by the same physics. So this is one of a tau. This is one of a tau lifetime. Okay. Actually, sorry. Let's put this on pause for a second, and let's go back to where I wanted to be, which was here. Okay. Pause. We'll come back to this question. Okay. So this is what we had without momentum relaxation. Now, suppose that momentum relaxation is irrelevant, so you've been treated perturbatively. Okay. So you add some lattice or some disorder to your theory, and then what you'll get is that this delta function, which remember has units of 1 over energy, right? Because you have to integrate this against omega to get 1. We'll come back to this. So what you get, if momentum relaxation is small, is weak, you get this formula, where this gamma is 1 over tau momentum relaxation. Right? It's the rate, gamma is the rate at which you lose momentum due to scattering of the lattice or of impurities. Okay. And now, so this is like a Judah formula, right? This is saying sigma goes like tau is tau. The naive Judah formula is the same thing with a lifetime in it. Okay. And often these things are basically the same quantity. They scale the same way with temperature. So often you can get away with replacing the lifetime. Okay, often you can get away with it, but it's not right. Okay. So again, to maybe be clear, so what's the picture here? You have a whole bunch of electrons. They're moving and they're carrying a current. They bump into each other. So any given electron will lose its momentum at some rate. That's this lifetime. But of course, it gives it to another electron that's carrying a charge. So the total current doesn't degrade. Right? But if the rate at which the electrons hit other electrons and the rate at which they hit the impurities of the lattice is comparable, and then you get the same answer. Okay. But again, technically to get a finite connectivity, you need these couplings. Okay. Blaise, do you have a question?
Yeah, I just meant to say that when you were talking about dangerously irrelevant, actually what often happens when you do the computation is that you get more modes than just the single mode you had without breaking translation invariance. And it turns out that these extra modes, which are turned on because you've broken translation invariance, are actually the ones that dominate the low energy physics.
Yeah, but we can.
So I think it basically says the same thing that what you were.
Okay, so let's just recap where we are. That if we're in some strongly coupled medium and we want to calculate the connectivity, we have to include, so I'm going to assume we're not in this case, okay? We'll stay away from localization and glassiness and insulators for now. Let's say that the lattice or the impurities are irrelevant or small. Then we can treat them perturbatively, and in that case we have this formula. This is the formula for the conductivity of some strongly interacting medium. Okay? It depends on the rate at which you lose momentum. Good. Now I'm going to give you a formula for gamma, and this will connect with the first part of this lecture. And so now, to begin with, let me specialize in the case of a lattice. Okay. So a lattice almost conserves momentum, actually. A lattice allows you to violate momentum, but only by k goes to k plus k lattice. Right? So with the lattice, the momentum is conserved up to the lattice wave vector. Okay, so if you bounce off the lattice, your momentum can change by some multiple of the lattice wave vector. Okay? You can prove this because it's still a discrete translation invariance. Okay? The lattice is periodic. So, what does this mean? This means that to lose, okay, now imagine the current you're driving through the system is a very low energy current. You want like DC conductivity, very low frequency. Okay, so all the electrons in the system are at low energy. Okay, and the only processes that degrade momentum happen at a finite k lattice. Is some microscopic thing, right? It's an angstrom, right? It's a short distance. And so, for this scattering to be efficient, the system will have to have many low energy degrees of freedom at finite momentum. Otherwise, it won't see the lattice. Another way of saying it, let's say you had bosons, relativistic bosons. As we saw in momentum space, all the low energy degrees of freedom are at the origin for a relativistic boson. And so if one of these guys scatters off the lattice, it'll get kicked over there, k lattice. But there are no low energy degrees of freedom over there. So this process is never going to happen. Okay? So a relativistic boson will just shoot through the lattice, and it will hardly notice that it's there. Because we saw that this low energy spectral weight, remember from this morning, was exponentially small. Right? So gamma, so for a relativistic boson, the momentum relaxation rate due to a lattice is exponentially small. Okay? Because all the low energy degrees of freedom are at the origin of momentum space. The lattice kicks them very off shell, right? And they don't want to be off shell, so it's unlikely. However, what about for Fermi surface? For Fermi surface, see, this is really a beautiful thing. In a Fermi surface, there are two momentum scales. There's kf, but then there's also kl. So what you can do, I'm going to simplify. Well, you can take an electron here and you can kick it over there by an amount kl. And as long as kl is less than 2kf, that's a low energy process, but it doesn't conserve momentum. Okay, so the reason that a metal, like copper, right? I'm talking about things. Well, the reason that some metals have a finite conductivity is because there are two momenta involved. Okay, there's kf, the Fermi momentum, and there's kl, the lattice momentum. Okay, and so the processes to degrade momentum are these lattice scatterings, but they can only work efficiently because the spectral weight is spread out and there exists low energy excitations at finite momentum. Okay? So it turns out there's a slight subtlety, but actually one is not good. It turns out you need to move two electrons at once. Okay? So this is called an Umklapp process. Okay, so Umklapp is a process where you take two electrons here and you move them over there. Okay? And that's described by a certain operator. So, yeah, I'll explain it now. So that's described by two electrons. You take psi dagger, psi, psi. That's a certain operator, right? And this operator can couple to the lattice, like up there, right? So cosine. Again, just imagine 1D. Okay, so this is a certain coupling in your field theory so in a Fermi liquid, in some theory of fermions, that doesn't conserve momentum. And it involves a 4 fermion term with the cosine of x in front. Okay, this mediates these kind of processes, and these can be efficient, right? Because these guys can stay at low energy. And what you'll find is a famous result that gamma the momentum relaxation rate goes like the temperature squared. Okay. This is the famous, well-known statement from the 1930s, so this is a modern language for it, that the electron-electron contribution to the resistivity of a metal goes like T squared at low temperatures. But that's only possible because that's actually related to the scaling dimension of this operator, and it's only possible because of these Matlab processes that don't conserve momentum. And they're only possible because of the Fermi momentum. There's a good reason you can't have one. Okay, so if it was just one, that would be that operator, right? The quadratic inside. And when you add this to the guy, to the action, it's still just a quadratic action. And so the theory would be free. And if the theory is free, everything's conserved, okay? So the conductivity is still infinite. So to degrade the conductivity, you need some kind of honest interaction, which means a non-quadratic term. Okay, so in the last 2 minutes, I want to tell you that this thing is a general result, sorry, it's a particular result of a general formula. So it turns out there's a general formula that's the following, that the momentum relaxation rate is, so let me put a G here. That's just the strength of this coupling. The momentum relaxation rate is the strength of the coupling to the lattice wave vector squared, times the limit as the frequency goes to 0 of the imaginary part, our best friend now, okay, the Vitali-Green's function, of the operator that couples to the lattice at 0 energy at the lattice wave vector divided by omega. Okay. So you can read, if you want, the derivation of this formula in this paper. But let me tell you why this is very, very, very extremely reasonable. Okay, so this says the rate at which you lose momentum is proportional to the strength of the operator that couples to the momentum violating term. It's pretty reasonable. It's some dimension thing. What is this? This is the low energy spectral weight, because omega is going to 0. Remember, we have to divide by omega because this thing is odd, so there's a spurious factor of omega that we don't care about. This is the number of low energy degrees of freedom at the lattice wave vector, right? And remember, the lattice wave vector, all the scatterings that degrade momentum happen at the lattice wave vector, right? So this is saying, how much stuff in the theory is there that sees the lattice? How many low energy excitations are there in the theory that can scatter off the lattice? And so it's not surprising that the rate at which you lose momentum is that. Okay. So let's do the semi-local critical case. So it turns out in the semi-local critical case, this thing, so the Fermi liquid, this goes like T squared. And in the semi-local critical case, this goes like T. So the Green function I wrote before had an omega. Remember how we had omega to the 2 delta K? When you heat it up, this omega just gets replaced by a T. Okay? That's what happens. So it goes like, and then you have to put an L there. So that's our answer. So the so the conductivity goes like 1 over gamma. The resistivity is 1 over the conductivity, so the resistivity goes like gamma. So the resistivity, oh, whoops, I know, okay. So the resistivity of a semi-local critical theory goes like, due to a lattice, goes like the temperature to some power that depends on KL. Okay. Whilst, again, if you have bosons, remember, the resistivity due to a lattice is exponentially small, e to the 1 over t. So the fact that these black holes have these low energy excitations with finite momentum translates into the fact that they have a reasonably large resistivity in the presence of a lattice. It goes like t to some power law t. Okay. Unfortunately, for phenomenological purposes, of course, what would everybody like to get, right? So T squared is the Fermi liquid. Many of these exotic materials have a linear in T resistivity. Okay? And so here what we've got is T to some funky power. Okay, that could be more or less anything. Very last comment, just about disorder. What about, so that's the resistivity to a lattice. What about disorder? So roughly, you can think of it as follows. A lattice is a single harmonic. It's cosine of kx. What disorder is a very complicated function. And one way to model a complicated function is as a sum of cosines with random phases. In fact, you can prove that if you sum a bunch of cosines with like this. This is a bunch of cosines with evenly spaced frequencies. Okay, 1, 2, 3, 4, 5, but with random phases. Okay, it will look like a disordered function, and it is a disordered function. So, in some limit, roughly, I don't quite have time to do this properly, but roughly, so disorder is like an integral over lattices. Okay. It turns out to be true. So, if you want to now take these, sorry, let me say one more important thing. So we got this answer. Okay, I didn't do all the calculations for you, but I promise you that getting this answer at most involves solving an ODE or two every now and then. Okay, you just do this matching calculation stuff. Now, if you want, what you can do is go away and solve the full Einstein's equations. Take the black hole, put a lattice on the boundary, and solve the PDEs in the presence of this lattice, and then run the current through it and numerically solve it. You'll get this answer. Okay, but we didn't have to solve PDEs. Okay, sometimes it's important to solve PDEs. Occasionally it's important, but it's always worth thinking before you solve PDEs. Okay, so you can. Okay, we just got the answer without. We didn't have to solve. We're talking about a completely inhomogeneous problem. Okay, but you know, there's physics that will get you to the answer. Right. Of course, when it's relevant, you have no option. Inhomogeneity is very important. But if inhomogeneity is irrelevant, you can do this perturbation